Classification of matter. Well, you'll notice as we go through the semester, scientists like to categorize and classify things. This is a little bit, if we stick with the Legos, you got a big pile of Legos. You could group the Legos in different ways, right? You could separate them by color, put all the red ones and all the blue ones and all the green ones. You could separate them by shape. You could separate them whether they're a regular tall Lego or they're one of the short Legos, all sorts of different ways you could categorize it. And so scientists do this with matter because it helps us to understand all these different things that we're looking at. We're looking for different things, for groups of substances that are similar. So first of all, what is matter? And that's a different question than what's the matter. What is matter? Matter is anything that occupies space and has mass. So lots and lots of things are matter. Your textbook, your desk, your chair, your body, all composed of matter. Anything you could put a sticker on is definitely matter. Can you think of something that is not matter?
Gravity.
Gravity. Antimatter. That's a good one. Probably, well, I don't know. I think that's still matter.
Technically, yes, it's just that whenever it comes into a regular matter, it'll annihilate it.
Yeah. You get matter and antimatter together. They annihilate it.
It's just that you don't like the actual matter.
Yeah, it's almost, yeah. Thankfully, we're not going to really talk about antimatter. Yeah, you can go over to the physics people for that. It's not for this class, no. What about love? Is love real?
Yes.
It's real. Is it matter? No. Does it matter? Absolutely. Love matters a great deal, but it's not matter. How about light? Is light matter?
At very least not in the same sense.
Not in the same sense. I mean, then we get into the quantum mechanics stuff, and you say, well, there's a particle of light. And so you could, if you get into the very small, then you could argue that. But in the general sense, no, light is not matter. Energy is not matter. But what about the air in this room?
Yes.
Yeah. We can't see it. We can't feel it unless we move it, and then we feel wind. But air does have mass, and it does take up space. How can you blow up a balloon? Why does it get bigger? Because you're filling it with air, and it's taking up space. Yes. So when we talk about a substance, we're talking about a specific instance of matter, a particular kind of matter. And we can classify matter according to its state or its composition. By state, we don't mean California, but we mean the physical form, and we'll talk about that. The composition is what basic components make up that matter. So let's look at the different states of matter. There's a fourth state, but we're not going to talk about it. So we can classify matter as a solid, a liquid, or a gas. And there's one substance that we are familiar with all three states of it, and that is water. Water in the solid state we call ice. In the liquid state, we call it water. And in the gas state, we would call it steam or vapor. So you can imagine solid water. The particles are very close together, and they don't move relative to each other. When you heat that up, you can change it from a solid into a liquid. You can melt the water. Other things can melt as well. Chocolate can melt. It's the one thing I can think of right now. So in the liquid, what's different here is the particles are still very close together, but now they can move. And so instead of sitting as little lumps at the bottom of this flask, the water now takes on the shape of the flask, although it's still sitting at the bottom. It has different properties. If we increase the temperature further, we can cause it to go into the gas state. We can cause it to evaporate. In the gas state, the particles are much farther apart. So in the solid state, the particles very close together, touchingly close, and they're fixed relative to each other. So there are also 3 states of matter for students. Right now you guys are in the solid state. We're all packed in here close together, right? But nobody's moving relative to other people. You're sitting or standing or leaning, and everybody's staying in the same place. Pardon me?
They're all right on the floor.
You may sit on the floor if you like, absolutely. I don't care. Are you all perfectly still? I hope not. I hope you're at least breathing, snoring, maybe. But you're all moving a little bit. Some of you are taking notes, nodding your head, wiggling, sighing, yawning, whatever, right? Everybody's moving a little bit. And that's what happens with molecules and atoms in the solid state. There's movement, but it's not relative to the other particles. So they vibrate, but they don't move around. So the solid has a fixed volume and a rigid shape. You take an ice cube and you put it in a bowl. You take that same ice cube and you put it on a plate. The shape of the ice cube doesn't change because all those particles are fixed relative to each other. Here we have a couple of examples of solids: ice, aluminum, diamonds. We can subdivide solids by how the particles are arranged. You can have a crystalline solid or amorphous. In a crystalline solid, we have order. I'd say on the whole that we have a crystalline solid of students right now because most of you are sitting on the stools at the benches. There's an order. And then we have a little bit of amorphousness around the edges. But there's a long-range, repeating 3-dimensional order, and that's characteristic of a crystalline solid. Other solids are amorphous. There's no shape. So if you think about kindergartners coming over to the teacher and sitting down around her for story time, are they going to sit in rows? No, they're just going to plop down wherever, right? And they're going to squeeze in between each other. There's not going to be any order. Kindergartners at story time would be amorphous. Amorphous means without shape. There's no consistent shape to it. So table salt and diamonds are examples of crystalline solids. Glass and plastic, rubber is another one. Those are examples of amorphous solids. The particles are not arranged in a particular way. In liquids, the atoms are still close together, but now they can move around. When we have lab and do experiments, we have the liquid state of students. We're still in the same room, but now you're moving about, milling about in the classroom. And so you're not always in the same position relative to the students around you. That's what happens in a liquid. The particles can move. And that's why liquid water takes on the shape of its container. If you put it in a tall, skinny glass, or if you pour it into a shallow dish, the shape changes, but the volume does not change. So liquids have fixed volumes, but their shapes are not fixed. The shape can change. The ability of liquids to flow is what makes them take on the shape of their container. The particles can move. Water, alcohol, gasoline are all examples of substances that are liquids at room temperature. And then we have gases. In gases, there's a lot more space between the particles. The gas state of students happens when class is over and you guys diffuse out the door and you go off in your separate directions. And we may be miles and miles apart from each other until we come back on Wednesday. That's the gas state. Free to move relative to each other and lots of space between. Because of that space, gases are compressible. So here we have 2 pistons. This piston has a liquid in it, and this piston has a gas. If we push down on this piston, this liquid, those particles are already touchingly close. They can't get any closer together. Nothing's going to happen. That's the principle that hydraulics works on. You have a liquid, like in your hydraulic brakes in your car, you have brake fluid, and you press on the pedal of your brakes, and that puts pressure on the liquid, the brake fluid, and that pressure gets transmitted to your brakes, where it puts pressure on the disc and slows your car down. Gases, though, have a lot of empty space between them. And so when you push down on this plunger, you can press the particles closer together. So the volume of gases can change, and the shape can change as well. So here's an overview of, some people really like flow charts. For those of you that like them, there it is. Some of you don't. This is an overview. I was thinking this was about the physical states. It's not. This is about composition. So we can divide matter into pure substances or mixtures. And then we have subdivisions under pure substances. We have elements and we have compounds. And under mixtures, we have heterogeneous and homogeneous mixtures. So that's an overview of what we're going to talk about next. So a pure substance or a mixture. A pure substance contains only one kind of particle. The composition of the substance is always the same. In a mixture, you can have different proportions of the components. Thinking of an example. So let's think about water. Water is H2O. So we've got, it's usually blue. So we've got an oxygen, and then we've got hydrogens. No, water isn't blue. What am I saying? Oxygen's red. Sorry, I'm having a brain fart here. So we've got one oxygen atom and two hydrogen atoms bonded together, and that makes water. Water is a pure substance. Pure water is a pure substance. All the particles in the water are exactly the same. One oxygen, two hydrogens. Always, always. Now, you can mix hydrogen and oxygen together, say fill up a balloon, and you could have equal amounts of oxygen and hydrogen, or you could have a little bit of oxygen and a lot of hydrogen, or vice versa. The proportions can be different. That's a mixture. But a pure substance is always the same. Water is always two hydrogen atoms to one oxygen atom. Doesn't matter where you got the water from. Okay? Within pure substances, there are two types. There are elements and there are compounds. And this categorization depends on whether you can break that substance down into simpler things or not. So an element cannot be broken down into simpler things. Something like helium. We're familiar with helium. You put it in balloons. It makes the balloons float. You inhale it. It makes your voice sound like Mickey Mouse. Fun stuff. Helium is an element. In that balloon, you have helium atoms. It's just all helium atoms. There's nothing else in there. You cannot break it down into simpler things. But a compound has two or more elements that are combined in a specific relationship. So water. Water is a compound. It has hydrogen and it has oxygen. And you can break water down into hydrogen and oxygen gases. That's something you can actually do at home. If you take a 9-volt battery and put it in a glass of tap water, what you'll observe is fizzing. Bubbles will form at each of the terminals. At one terminal, you'll be forming hydrogen gas, and at the other terminal, you'll form oxygen gas. The water can be broken down into simpler substances. Hydrogen and oxygen are each elements, and you cannot break those down into simpler things. We can categorize mixtures. We divide them into two different categories, heterogeneous and homogeneous. And we do a lot with prefixes and suffixes in chemistry. And here we have the prefixes hetero and homo. And hetero means different, and homo means the same. So a heterogeneous mixture, it does not mix uniformly. you look at it and you see chunks or lumps or bumps, and it's not all the same. A homogeneous mixture appears to be a pure substance. It looks like a pure substance, but it's not. I think I have examples. Yeah. So in the heterogeneous mixture, the composition is going to vary from region to region. An example of this is salt and sand. You mix salt and sand, and if you look at it closely, you can see the salt crystals and you can see the sand particles, and they're not thoroughly mixed. You could pick out the difference between them. If you mix oil and water, you can shake it up all you want. As soon as you put it down, the oil comes to the top, the water settles to the bottom. There's two parts to it, and their composition is different. Now, if you mix alcohol and water, it'll mix together. There's no layers, and the composition at the top, in the middle, and the bottom of the glass will be the same. That would be homogeneous. Heterogeneous, there's different parts in it. So heterogeneous, different. Homogeneous is the same throughout. You put sugar in your tea. The sugar dissolves in the tea, and it spreads throughout, and the top is just as sweet as the bottom. It's homogeneous. Homogeneous mixtures have uniform compositions because they mix uniformly. Heterogeneous mixtures do not have uniform compositions. Mixtures can be separated because they're two different substances just mixed together. They're not chemically bound to each other. They can be separated. And the way we separate mixtures is based on either their physical or their chemical properties. If there's a difference in the properties, then we can separate them. And separating mixtures can be a very big challenge and something that we need to do sometimes. And so there's a lot of different techniques for separating mixtures. If you have sand and water, how can you separate the sand from the water? You could filter it. If you just let it sit for a bit, all the sand will go to the bottom, right? And if you're really gentle and careful, you could pour the water off the top. That's called decanting, when you pour a liquid off the top of a solid. Now, it may not be the best way to completely separate the two things, but it's certainly an easy way and doesn't require much equipment. So that's one way to separate those. We're separating sand and water based on differences in physical state. One's a solid, one's a liquid. If you have a homogeneous mixture of liquids, this is more challenging to separate. A heterogeneous mixture of liquids, like oil and water, well, you could decant, you could pour the oil off the top, or use a syringe and suck it off the top. You could do that. But if, like, you have alcohol and water and they're homogeneously mixed, how do we separate those things? Well, one way is by distillation. And this makes use of differences in boiling points. Alcohol has a lower boiling point than water does. So if you heat a mixture of alcohol and water, the alcohol will evaporate first, and you can collect that. And in distillation, the way that's done is you put the mixture in this flask, you heat it. The alcohol is more volatile, it's more easily vaporizable, it has a lower boiling point. That will come off as a gas first, and then you don't let it just escape into the room. You collect it by channeling it through this condenser. This has an inner sleeve and an outer sleeve. And between those, we run cold water to cool that gaseous alcohol down, to condense it. And then it drips out down here, and you can get pure alcohol down here. So that's distillation. You've heard of moonshine, right? And guys out in the woods with their still, right? And they're boiling mash, and this is what they're doing. It's just not so fancy. But they're distilling this mash that they've fermented stuff to create alcohol, and they're distilling it to get the alcohol out. There's some dangers associated with that. It's not something you should try at home. Another way to separate mixtures is by filtration. You do this when you make coffee in the morning, unless you're making instant coffee. We'll have to talk about that. You do this when you make spaghetti. How do you separate the spaghetti noodles from the hot water? Use a colander, a strainer, right? You pour the whole thing into this colander, a big bowl with holes in it. The water goes through because it's liquid. The spaghetti stays in the colander because it's a solid. This is what filtration looks like in the lab, chemistry lab. We use a piece of paper, much like a coffee filter, and you pour your mixture into that. The liquid will go through, and the solid will remain behind. That's filtration.